Hello, let's talk about horizontal asymptotes, 2.2a. All right, these occur when the limit as x approaches infinity of f of x equals some number, or the limit as x approaches negative infinity of f of x equals some number. Functions may or may not have up to 2 horizontal asymptotes. Functions can touch them, contrary to popular belief. And horizontal asymptotes are in the form y equals some number. So visually, say we have a coordinate plane, and let's say our horizontal asymptotes looks like this. Let's say the function does that. So then as x approaches infinity, this function is approaching that asymptote. Maybe it looks like this, where that's the worst asymptote I've ever seen. All right, let's try that again. See if I can make it look like it's, kind of like a line. All right, let's say that's our horizontal asymptote, and maybe our function is approaching like that. Okay? Our first strategy for finding horizontal asymptotes is use limits that you know. So you should know the limit as x approaches infinity of x equals infinity, okay? Because if you just have a function x, as x goes to infinity, so does the function. The limit as x approaches infinity of 1 over x is 1 over a super big number, which is going towards 0. The limit as x approaches infinity of sine x over x equals, so we talked about the limit as x approaches 0 for sine x over x. And if you recall, I believe I drew a lovely picture of sine x over x is going up like that. So as x approaches infinity, this should be hovering more around the x-axis, the function goes to 0. Because basically as x approaches infinity, it's just hovering around the line y equals 0. And the limit as x approaches infinity of e to the, of e to the x, well, e to the infinity is just infinity. So the limit as x approaches infinity of e to the x is infinity. You should memorize these. So for example, if you have the limit as x approaches infinity of 5x plus sine x over x, if you look at it, it's kind of like infinity over infinity, sort of, so we really can't do anything with that. So we're going to have to simplify. So this is the same as the limit as x approaches infinity of 5x over x, so we're just kind of splitting it, plus the limit as x approaches infinity of sine x over x. You'll notice I keep writing limit until I evaluate. So this is the limit as x approaches infinity. Well, 5x over x is just 5, plus the limit as x approaches infinity of sine x over x. The limit as x approaches infinity of 5 is just 5. The limit as x approaches infinity of sine x over x is 0. So our answer is 5. And this means we have a horizontal asymptote at y equals 5. So that's what we found when we did that limit. Let's do another example. The limit as x approaches infinity of e to the negative x over x. So this is the same as the limit as x approaches infinity of 1 over x times e to the negative x, which is the same as the limit as x approaches infinity of 1 over x times the limit as x approaches infinity of 1 over e to the x, because e to a negative power is just 1 over e to the positive power. The limit as x approaches infinity of 1 over x, 1 over a really big number is 0, times 1 over e to the x is just 1 over e to infinity, or 1 over infinity, so that's another 0, and 0 times 0 is just 0. And that is a horizontal asymptote at y equals 0. Here's another. Let's say f of x equals x over absolute value of x. If we split it into our piecewise functions, we have x over x when x is greater than 0, and we have x over negative x when x is less than 0. So that's just kind of our prep work. Now, if we want to find the limit as x approaches infinity of x over absolute value of x, as x goes to positive infinity, the limit, this is the same as the limit as x goes to infinity of just x over x, because we're using this top function here, which is the limit as x approaches infinity of 1, which is just 1. Whereas if we find the limit as x approaches negative infinity of x over absolute value of x, limit as x approaches infinity, this is x over negative x. Oh, I forgot a fraction bar there, sorry. X over negative x, okay? Because as x goes to negative infinity, that's definitely less than 0. And this is the limit as x approaches infinity of negative 1, which is negative 1. So this is sort of a weird one, because the way this function will look is when x is greater than 0, it'll look like y equals 1. And when x is less than 0, it'll look like y equals negative 1, like this. So it's kind of a weird sort of asymptote, because as x approaches infinity, it just looks like 1, and as x approaches negative infinity, it looks like negative 1. But the logic sort of still works. Sorry, I don't have a less wishy-washy explanation for that one. Our second strategy for horizontal asymptotes is end behavior models. And essentially we look at the dominant terms. For example, the limit as x approaches infinity of 2x cubed minus 3x squared plus 1 over x plus 3. As x goes to infinity, basically is the number, as x gets really, really big, the only terms that matter are these leading terms, 2x cubed and x. So then our end behavior model, 2x cubed over x, is 2x squared. So it's the function y equals 2x squared, which is a parabola. And if our end behavior is a parabola, then we have no horizontal asymptotes. For another example, let's do the limit as x approaches infinity of 2x to the fifth plus x to the fourth minus x squared plus 1 over 3x squared minus 5x plus 7. Again, if you zoom out really far, the only terms that matter are these two. So our end behavior model is 2x, it's not really an equal sign per se, 2x to the fifth over 3x squared, which is 2/3 x squared. Nope, 2/3 x cubed. 5 minus 2 is 3. So the function y equals 2/3 x cubed looks something like this. And so once again, there are no horizontal asymptotes. For our final example, we have the limit as x approaches infinity of 2x cubed plus 7x squared plus 15 over 3x cubed minus 19. Leading terms, 2x cubed over 3x cubed, which simplifies to 2/3. So our end behavior is just the function y equals 2/3, meaning we have a horizontal asymptote. Sorry for the delay. At y equals 2/3.